We found last day that this magnetic force has a magnitude proportional to the charge, the part of the velocity perpendicular to the B field, and the strength of the B field. And we can make the constant of proportionality 1 if we express the magnetic field in units of Tesla. And that's what we do. Those will be the official units of the magnetic field. Now, it's that V perp that I want to look at for a moment. If that's my magnetic field, and that's my velocity vector, we're used to breaking up vectors into x and y components. But here what I'm going to do is I'm going to rotate the coordinate system so that it's relative to the magnetic field. I'm going to look for the part of this vector that is along B and the part that is perpendicular to B. The way I do that is I draw a line perpendicular to B that goes to the end of my velocity. I then break up my vector into the part that is parallel and the part that is perpendicular. There's my right angle. Okay? So I no longer am using x and y, I'm using parallel and perpendicular. Now it's only that perpendicular part that enters into my equation for the force. And I can see that that's the total speed, v, times the sine of the angle between these two important vectors, the velocity and the B field. Now, that gives me this equation for the magnetic force. And we often call this the Lorentz force. Again, to honor a very prominent and yet dead professor. Now, Professor Lorentz is also known for the Lorentz transformation, which is the foundation of Einstein's theory of relativity. So, way smart guy. Okay, now you're going to be using this formula. Oh, what direction would this be before we move on? This gives me the magnitude. The direction is given by that right-hand rule number 1. Reach in the direction of the motion, turn your wrist so that you can wave in the direction of the B field, and it would be out for a positive charge. Out for a positive charge.